One day in the near future, I very much anticipate the world observing large blimp-like airships sustaining our renewable future on all habitable continents, or completely new cities across the globe via this technology.
This is EnergyCast, and I'm Jay Downhauer. Today we're talking about harnessing hydropower from the clouds. It's one of the more radical concepts I've seen, but so out of the box that it just might work. The core concept can be found in a common household appliance, a dehumidifier. Now, they didn't have these in Louisiana where I grew up. I wish they'd had one for the whole state. It's my understanding that many of you folks up north in your basements use these. That's also something we never saw in the Bayou State. Dehumidifiers produce water as a byproduct. My guest has figured that if you could hang a dehumidifier in the sky and shoot the water back down to earth, you could run a turbine and provide fresh water. So how does he want to do that? A tower? A drone? No, with this. Yes, he wants to load up an airship with air intake fans, heaters, dehumidifiers, and water containers. Then he would tether to the earth a water tube. Once there's enough water, the water would then be poured through the tube to the ground and run a hydroelectric turbine. The water once on the ground would be used for municipal or agricultural use. Now, some of the power generated on the ground would then be sent back up to the airship to run the equipment. My guest says that an airship producing 1,000 gallons a minute could produce a net 5 megawatt hours of energy, about as much as a large wind turbine. Depending on the cloud cover and humidity, the process may be a little intermittent, but there are some other benefits as well. Namely, my guest says they believe they can help with some unique air pollution issues. In Utah, where they're testing their first setup, parts of the state are dealing with an inversion zone, where pollution is trapped under a warm layer of air. Using filters on the ground, that moisture can be cleaned up and made available for use. It's a process that's half power, half water treatment, but 100% unique. My guest today is Chaac co-founder and CEO of Chaac, a startup based in the Salt Lake City area. Chaac and his partner Sam Kimsey have been running Chaac about a year and are about to begin test operations out in Utah. The name Chaac comes from a Mayan god of rain. Using his lightning axe, it says Chaac strikes clouds to make lightning and rain. In Chaac case, they hope some heavy-duty airborne dehumidifiers are going to make a little hydropower. Chaac is an 8-year Army veteran and says he got the idea while watering his plants of all places. I hope you enjoy my conversation with Chaac. We're here with Chaac, co-founder and CEO of Chaac Technologies. And Chaac, you told me you got the idea for this while watering your plants. How'd that lead you to this?
Yeah, so I had a dehumidifier in my basement while living outside of the D.C. area in Northern Virginia. And I just wanted to understand a better way to repurpose condensed water through a dehumidifier that I had. Pouring the condensed water down a drain is incredibly energy exhaustive for water treatment operations. So that option seemed to be a completely non-efficient approach for water reclamation. And while I was actually designing a secondary approach to rectify me carrying a water bucket from my basement every day in the summer months where it's incredibly humid, I was actually designing a water pump apparatus to place inside the dehumidifier water reclamation bucket to initialize and trigger upon reaching a certain level. But I realized that would also be incredibly power exhaustive. So it was really, I walked out of my back door and I observed a very large cumulonimbus cloud hovering right above DC. And honestly, it was an epiphany moment of how can I condense this? I can use falling water via gravity at 9.8 meters per second to condense water vapor and turn the velocity of water from mechanical energy directly into electrical energy using hydroturbines at a ground control station. And honestly, that day, I pivoted immediately and began writing the white papers, which soon morphed into now 3 non-provisional patent applications with the USPTO.
Now, one of the things is, yes, you can pull water out of clouds, but you were kind of talking about this in terms of need in arid places, but arid places aren't too humid, are they?
You're absolutely right. If we're really trying to target an arid market primarily, the humid area for these operations to work, and that was actually by design from the initial core technology in the drawings. I know this technology will work perfectly and flawlessly in high humid areas, but I actually wanted to take it a step further, and clearly there's a water shortage problem in arid areas. That's why they're arid. And how can we actually terraform these areas on Earth into vegetative landscapes? And to add even more complexity to all geographic regions, humidity levels vary in altitude. Total measure of water in the atmosphere resides in a dynamic Goldilocks zone depending on cloud formations and temperature. What I was looking at is how could we operate all of our designs in regions with an approximately 40% relative humidity or 5 grams water vapor per cubic meter absolute humidity or higher. And it turns out that's actually what we did when we moved to Utah for that very reason. And so in short, it does take a bit more exhaustive power supplies with our onboard aerial compressors and our airships, but that's actually by design so that we can have self-powered generative technology in these areas by condensing these cloud formations. And cloud formations clearly have more of a condensed water vapor naturally in their formations.
We talked about this earlier, but how much water can you get from your process?
This is actually very fascinating. I was looking more into accumulations of native clouds and how much water vapor they contain. On average, a cloud has a volume of 1 billion cubic meters of water vapor. Well, that yields to approximately 30 million liters of available water, which equates to around 8 million gallons. And so there are several factors to consider there. No cloud is the same. Clouds are constantly moving, while our airborne atmospheric water generation platforms remain static. Though there is more of an abundance of water to be harvested directly in those cloud formations, a relative amount for native atmospheric humidity is combined in our system intake approach. This really will come down to our intake rate, which can vary from 20 gallons per minute to our operational goal of 4,000 gallons per minute to condense enough water vapor to produce the output of a true and clean renewable hydropower.
Up to 4,000 gallons a minute. Would that be from a single blimp, or would that be from
just from one blimp, just from one airborne AWG system?
Yeah.
So it's incredible, but we can do it.
Right, because I was thinking about this today. It's like, yeah, he's going to hang a blimp up in the sky. And you can get it at the Home Depot, that 3/8 clear vinyl tubing, but you cannot run 4,000 gallons through that. So what kind of tubing would you be running a single airship down to the surface?
So I can tell you it would not be a 1/4-inch tubing. We're prototyping anywhere between a 6-inch diameter tubing all the way to 24 to 36 inches, depending on the airship length and width of the specs. It will be a pretty exhaustive, flexible water tubing that we're going to have to custom build.
That's pretty amazing. And I'm thinking of a very large blimp, like a Goodyear blimp, right?
Yeah. So in short, it very well could be up to 250 feet in length, actually larger than the Goodyear blimp that was deployed right now. It will be a rather large airship for a minimum viable product once we deploy them. These will not be the small RC blimps that we can put out at table length. These will be mini-mall sized.
Well, Jake, we talked about how big these blimps can get, but you're saying it doesn't necessarily have to be that big. What do you think would be the sweet spot?
So the ideal rate, without just saying more the better, would be around that 4,000 gallons per minute Goldilocks window zone. What we don't want to do is intake an absorbent amount of water without the necessary water vehicles to service those markets. For example, if we were to intake 8,000 gallons per minute, would a local grid infrastructure be willing and able to handle the load balance of servicing the absorbent amount of energy through 500 and 345 kV lines? Most likely not.
Look, clouds pass over, humidity changes from day to day. So do you think you would see a steady amount of power and water, or would it be intermittent? What do you think the models are showing that would look like?
So our models right now indicate varying levels. As clouds will pass through these airships, the intake level will vary based off of that absolute humidity level. And just from a percentage of a relative humidity perspective, 40% or higher will still be able to throttle those rates collectively. So it will be relative depending on the actual environment in the area. But if it's high humid areas by 80%, 90% above relative humidity, we will be able to convert a higher absorbent amount of sustained continuous power to achieve that 5 megawatt hours continuous power goal.
Okay, cool. How high up would they be?
We require 1,000 feet for our minimum deployment zones. But if in higher elevations, especially in higher elevations bordering mountain ranges, clouds generate friction natively against these mountain ranges. And what we can do is actually harness that a bit. And that's why our first project site is in western Utah, where we purchased a mountain for that very reason. And so we can actually deploy the airship natively on top of the butte that we purchased without having to be 1,000 feet from that butte top. But the native drop sheer down is approximately 1,200 feet. So as long as we're 1,000 feet or higher, we'll be able to accumulate enough gravity and hydrostatic pressure to innervate our energy conversion process.
And basically, the blimp is up in the air and it's collecting humidity or water vapor, the clouds going by. How's is it picking it up?
Imagine this lighter than air vessel or this blimp-like structure hanging in the air with an array of air intake fans surrounding it. Our prototype will have just a few for a benchmark and prototype test, but our MVP will have over 100 air intake fans, which will constantly be intaking warm water vapor through a process through evaporator coils. And those evaporator coils will heat that surrounding air temperature before it is condensed on the condenser coils, which therefore is running a refrigerant through an onboard compressor. Similar to what is already deployed right now in dehumidification appliances in basements throughout the New England area in the U.S. Throughout the Airship, there will be a series of water bladder pockets to accumulate enough water that once the water has risen above a certain point, then it will be released through the water tubing chamber all the way down statically to the ground control station.
You know, I can see a lot of different ways where you could power the blimp, especially if you're going to run a water tube all the way to the ground. You could almost run a power line up to the top. Run that with your own supply if you wanted to. How would you power the blimp?
You hit the nail right on the head. Yeah, there can be an easy transmission line routed directly into the Airship, powering onboard capacitors for onboard compressor, all the air intake fan batteries, as well as any supplemental heating low-powered element so that we can minimally heat the surrounding area to innervate the intake process quite more substantially, more so than cold air. Cold air is a bit harder to intake. It can freeze some of the evaporator coil lines and clog up the air intake fans. And so by design, we were looking at sourcing at low-power heating elements to place around the aircraft. If indeed in cooler temperatures, we could activate these through the onboard capacitors powering onboard the Airship, which is actually quite unique.
The Airship, do you need a captain? Does there need to be a person on the blimp?
No one needs to be on the blimp at all. It will be static. I'm sure that certainly could be arranged later on. It will be completely via remote sensing.
So basically what's happening is we're collecting water. The water is rushing down through a tube. It's running a hydroelectric turbine on the ground, just flowing directly to the turbine, correct?
Yeah, that's correct. The ground control station will have onboard transformers as well to convert the direct current to AC, and therefore pipe the transmission back into the limp-like vessel. Yeah, that's exactly how it will work. You hit the nail right on the head with hydrostatic turbines being located on the bottom of the water tubing, and the filtered water that we will have activated carbon filtering located along the water flexible tubing flowing down to the ground control station. And that's actually the byproduct of the yield result, is that we are a net carbon-free hydropower industry. The water will hit the turbines, produce enough electricity through alternating current to convert the mechanical energy into the direct electrical energy. The onboard transformers will then convert the DC to AC to service ubiquitous markets, and the byproduct is clean, fresh water.
Have you built a prototype yet, or that's about to happen in Utah?
It's about to happen. We're building it now. We're actually building it in several different places, which will be deployed for the first deployment location here at our project site, which is a very interesting location as we're right next to a step-down substation.
Oh, cool. And since when we spoke earlier this week, you said you think you can make 5 megawatt hours of continuous power. That would be if you got to your full-size 4,000 gallon per minute, that would work to 5 megawatt hours. Am I doing that right?
Actually, our 5 megawatt hours of continuous power comes from a rather conservative estimate, just shy of 1,000 gallons per minute. The 5 megawatt hours of continuous power does factor in the power loss, or the power being redistributed back into the Airship to provide the yield output of 5. So with 1,000 gallons approximately per minute of air water vapor intake for condensation, we'll actually produce more than 5 megawatt hours of continuous power.
Okay, so that's net out. So that's good.
That's correct.
You mentioned that you would be running the water through a carbon filter. I would be surprised that it would even need that much. How much cleanup really does it need?
It really depends geographically. So in the Salt Lake Valley, is that the valley is plagued by a process known as inversion, where cold air and pollutants from vehicle exhaust and harmful carbon emissions are trapped under a warm layer of air, and cold air trapping all the harmful carbon emissions doesn't escape. We would have the ability to condense inversion completely and eradicate it. And so condensing those harmful pollutants, that would require an absorbent amount of activated carbon filtering to filter out all the argon, the nitrogen, the hydrocarbons. However, in areas where there's not so much of that, the water wouldn't require much activated carbon filtering at all.
I'd assume this would have a lot of potential, and I talk about this a lot. This would have a lot of potential in the developing world, islands, places without conventional utilities.
Yeah, you're absolutely correct. Developing worlds do require a need for fresh water and clean hydropower. And just put it in perspective, to back up a bit, there's over 844 million people, according to the World Health Organization, living without access to fresh water. And those with power in the developing world are most likely using energy from harmful carbon emission plants. So in addition to the developing areas and islands, we could also support military operations for soldiers, Marines, airmen, sailors, and Coast Guard servicemen and women deployed in remote locations with renewable hydropower and fresh water using our highly mobile, self-sustaining power generative airborne platforms.
So Jake, you're in startup mode at this point. This is always a very exciting time to be doing this. There's so many possibilities. Who is showing the most interest at this point? There's always people who come out of places and they always are surprised. So who surprised you?
So certainly exciting times, to say the least, Jay. We're observing a high interest primarily in clean energy consortiums across the globe, cooperatives in the local region of where we're at in Western Utah, and other power producers. As once a party is interested and those equities connect the dots on what we're presenting to them and describing our technologies, the response is generally more times than not, and I quote, okay, this is pretty cool and game changing. And when we hear that, that's certainly self-reassurance of where we're at in the exciting time.
We focus a lot on business here. Just curious how you guys got your seed money to do the initial project, how you funded that.
So everything to this point has been bootstrapped. We have bootstrapped everything in our operations to include purchasing the project site, purchasing all the patents, restructuring the corporations, all of the corporate counsel fees. Everything to this point has been 100% bootstrapped in our company.
No angel investor just wrote you $1 million check?
Not yet, but I will be more than amenable and open to that if there's an angel equity out there that is interested or intrigued on our project.
Yeah, my joke is always that angel investors wouldn't finance the wheel unless it had 3 years of finance.
Yeah, that's nearly been our experience. Seems like you've seen this play out a lot over the years.
Seen it a little bit. Sometimes investors and people, when they're trying to wrap their heads around a technology, they go, are you an energy provider or are you a water provider? And I know that sounds silly to people, but it's kind of true. People get a little bit confused if it's not very simple what your market is, right?
Yeah, and it's certainly an interesting discussion point when I'm talking with investors, potential partners, is how do we really describe ourselves? We provide an abundance of both. Most folks would consider us an energy services company, or we're an ESCO. Some other ones would consider us more what we truly are, would be an individual power provider, especially within the renewable energy providing space. To others, we would be an abundance of a fresh water provider. It's interesting on how we frame hybrid form of that. Some of the easiest conversations I've had is that, well, we can also be constituted as a utility technology corporation, not your traditional brick and mortar utility, but a renewable utility technology organization.
You said you were in DC, but you moved to Utah. I'm just curious, it was humid there. Why would you move to Utah? What was the reason for that?
So what I was looking at is what state has a severe water shortage, soil and with drought conditions? What state has harsh humidity levels that will prevent general technologies like this from working? Welcoming to renewables and consist of a harsh air quality index. And it turns out that the Beehive state in Utah is the perfect candidate.
And they've got great jazz. Yeah, I'm from Louisiana. There was a joke one time. It was like, we're going to name our basketball team the New Orleans Mormon Tabernacle Choir.
Well, that's nice right there. Yeah. Hey, we got a great choir out here, so there's that.
Okay, Jake, I'm going to finish with a lightning round of your thoughts on different energy technologies, starting with natural gas.
Organic methane, more harmful to the atmosphere, more power to produce, to process, and non-renewable.
Crude oil.
High energy density, toxic hydrocarbon emissions, also non-renewable.
Nuclear.
Abundance of hydrogen, high energy density of fusion reaction. However, the facilities are not fully renewable during manufacturing and construction.
Coal.
Potentially high carbon emissions. However, great secondary carbon industries, rapid grid availability and economic gain.
Wind.
Geographic dependence, intermittent, costly for manufacturing, deployment, mobility, also very highly renewable.
Solar.
Non-environmental friendly production, increase in carbon footprint for manufacturing, and photovoltaic salt accumulation impact negative for the environment.
Biofuels.
Food security impact, high hydrocarbon emission for production.
And we're going to break this into conventional hydroelectric and then you guys. Conventional hydroelectric.
Abundantly available, but within limited geographic resources. Reliable within the technology that we use today.
And then your hydroelectric technology.
Highly abundantly available with water floating right above us. Highly renewable and highly self-power generative.
Geothermal.
Minimal emissions, continually reliant, possible thermal depletion.
Energy storage.
Incredible need for accelerated advancement, but enjoy hydro pumping, flow batteries, thermal batteries, compressed air storage, all revolutionary advancements to prevent energy dilution.
Electric vehicles.
Need for global infrastructure. We need better renewable or continuous charging power to support electric vehicles at scale.
Energy efficiency.
Lots of room for growth, machine learning applications, and distributed micro power load balancing.
And then finally, fusion power.
Yeah, extremely high temperatures required, low fuel costs, but could produce a net negative carbon reduction.
All right, Jake Hammock, Chaac Technologies, thank you so much for your time.
It was an absolute pleasure, Jay. Thank you so much for having me.
That was Jake Hammock, co-founder and CEO of Chaac Technologies, a startup in Utah. Since we spoke, Jake says they're now considering using thermal energy from the systems on board the Airship to sustain flight. They're also developing a cargo containerized unit for deployment to developing nations, disaster areas, and for the military. I want to thank Jake for reaching out and sharing his incredible technology with us. I wish him and his partner Sam the best of luck on their pilot. You can find plenty of pictures on energy-cast.com as well as on Instagram at Host Energy. All guests are sent the raw and completed audio the week of release. So far, no complaints. Be sure to leave us a positive review on iTunes. That gets the word out. Music was produced by Sean Stroop at Stroop Loops. That wraps up episode 61. Be sure to join us next week when we talk a little geothermal policy with the Department of Energy. You won't want to miss it. Until then, I'm Jay Dowenhauer. We'll see you next time.